Okay, so thank you, Guan, for the invitation, and hello all. It's very nice to meet everyone, even it's not in an in-person session. So my name is Emrecan Demirörs, as Guan introduced greatly. So today I will be talking about some of our recent works and some of the fundamentals of the research that we're doing here at the Institute for the Wireless of Internet of Things at Northeastern University. The title of my talk is going to be Towards Software-Defined Underwater Networks, and this is some of the research that I've been doing in collaboration with Professor Tommaso Melodia and some other collaborators like Professor Stefano Bazzani, Denis Ünal, Kerem Enos, and Daniel Uvedo. So without further ado, let me go and explain what is underwater network systems and why do we need them. So I'm not sure how many of you are familiar what is actually underwater networks are, or what is underwater acoustic networking can be used for. It's not something very explicit when you first hear about it, what this could be used for, but actually it is a key enabler for many technologies, and it will be a much more commonly used technology in the future, especially with the rise of blue economy and blue technologies that picking up in this decade. Some of those applications that can be enabled with this unique technology is can be military or civilian. This could be underwater surveillance, so you can do surveillance in the ports or different shipyards, both for military and both for civilian purposes. You can do offshore equipment monitoring. This could be for the offshore equipments that is like the old type of equipment that is oil and gas industry, offshore platforms, or this could be a new generation of offshore infrastructure like offshore wind farms. So you can actually deploy those networks to be able to do sensing and do monitoring in real time. Another application that is getting heavily enabled by this technology is aquaculture and environmental monitoring. There is a huge seafood deficit today here in US. So the US seafood deficit is around $16.9 billion. So we are importing more seafood than we are actually consuming every year. So in order to change that, there's quite a bit of work and quite a bit of initiative going on from both from the industry and both from the government. So there are some solutions like data-driven fish ranges, which will increase the efficiency of aquaculture and the fish industry. There are some other applications like cage monitoring or marine life monitoring that you can actually do pollution tracking and other applications like that. So there's tons of different applications, and there will be more and more applications as the technology picked up by the industry. So as you can see, there's many different applications, many different end users. This could be Navy, this could be some owner of a fish ranch up in the Maine or in Vermont, where they have like small fishermen. So there are different applicational needs, and there's different system needs. So the problem of it becoming very complex and diverse. So you cannot just have one solution that fits all problem. So you need to have different type of flexible solutions. Also, to emphasize a little bit of the importance of this technology, a recent announcement from the US Department of Defense, they have announced a notion called Joint All-Domain Command and Control. So this notion or paradigms specifically is looking for a network of sensors composed of autonomous mobile and wirelessly connected aerial and underwater devices, which can create different applications. So what it means is that you might not need buoys that is connecting the underwater devices and aerial devices, but you can connect them and create some multi-domain applications to achieve a common goal. So you can imagine having multiple unmanned vehicles, both in underwater and both in air, doing one specific operation. So these are all different applications that you can think of that that plays a role in the current applications. However, when you look into the underwater acoustic channel, it's not as straightforward, or it's not as similar as what we have in the radio frequency waves. I think to start with, it would make sense to explain why we're not using radio frequency waves in underwater. So to give you a sense, radio frequency waves are conducted in the seawater. It's pretty much like how your microwave oven is working, right? So when you put microwave or RF waves to an aqueous medium, which could be your body, it could be the food that you're heating up, or could be the ocean, then things are getting heat up, everything is conducted, so nothing is actually propagated. So the RF waves are severely attenuated with the ocean water, the lake waters, all types of ocean environment. And that's the reason why we cannot use RF technologies like Wi-Fi, Bluetooth, or our 5G, 6G, or the current 4G devices to connect different things in underwater. So in a sense, we cannot realize Internet of Things in the underwater domain without using the acoustic waves, which is pretty much what is inspired from the nature. It's what marine mammals are using to communicate, or what has been used by Navy over those past decades for detection and doing sonar applications. So looking into the acoustic channel, even though it might sound straightforward to use acoustic signals, which is pretty much the sound waves that we used in air as well, and the way that we're communicating with each other, they're actually a way unique channel compared to the RF waves. So there is high path loss, even though it is the best modality that can be used in underwater. It still suffers from high path loss. It has a unique noise. And you can see actually here on the right-hand side, the types of noises that appears in different parts of the frequency. So it has a colored noise, which each frequency could have a different type of noise source. And these noise sources will change, especially and depending on what location that you're deploying, or at what time you're deploying, because these are created by turbidity, waves, if there is a marine mammal is passing by, or shipping noises, which can be quite varying. So looking at all these, it's a very challenging channel. And on top of that, it's actually has a very limited bandwidth. So when you're talking about RF waves, for example, if you're talking about like Wi-Fi technologies, you're talking about you're transmitting 20 megahertz bandwidth over 2.4 gigahertz center frequency, right? When you are doing underwater communications, we're talking about kilohertz of bandwidths. And if you're like really pushing to the boundaries, you might have hundreds of kilohertz frequencies over hundreds of kilohertz center frequencies. So it's actually a wideband problem, which can get really complex to solve. And because it is also very much band limited, you need to use your bandwidth quite efficiently, because you have no resources to be thrown away. And another aspect that is, which I think I don't have it on this slide, is the delay spread. So there is a huge delay spread, because this is not the speed of light like we have it. This is actually multiple orders of magnitude slower channel. This is 1,500 meters per second sound speed profile in the underwater as a flat. So it's much slower than what we have with the RF waves. So it's actually a million times slower. So it creates different type of challenges. So seeing all these challenges and then understanding that everything is actually temporal and spatially varying, it is not a, it's not intuitively you can think of, we would need reconfigurable and programmable architectures to adapt the devices itself to satisfy this varying environmental and application needs. So we have different application needs, we have different system needs, and then we also have a varying channel. So it is basically very important to have reconfigurability and programmability that can be implemented in real time. When you look into today's underwater technologies, what is out there, there are many limitations. Unfortunately, the technology is not sufficed adequately addressing all these requirements that I just mentioned. If you look into the modems and hardware out there, most of those devices are monolithic architecture, so they have hardware-based devices. So you cannot update, improve, or reconfigure them, neither in real time nor in offline as well. They are mostly proprietary architectures, so you cannot develop or implement new protocols on them. If you want to try or you develop some new protocols, there is no way that you can try them on the existing modems. It has lack of plug and play solutions. Most of those modems have been developed with some other military systems in mind. So there is not much plug and play solutions that you can actually get it and test it with some other systems that's out there. They're also not size and cost efficient, and they're mostly has limited energy efficiency. But I think that most importantly, most of those devices are focused on getting low data rates. And typically these low data rates are much lower than you can think of. It's like 10, you're talking about like typically lower than 10 kilobits per second. So this is thousands of times slower than what we are using in RF waves with our devices. That is pretty much what we're taking for granted in our daily lives in terrestrial environments. There is also quite a bit of limitations in terms of network abstractions. Most of the devices out there is working like walkie-talkies. So they're primarily designed as point-to-point devices. They are lacking network abstractions or lacking the implementation of cross-layer control algorithms, so you cannot adapt or configure your medium access control and network layer protocols or physical layer protocols in a cross-layer fashion. They have limited spectrum agility, so they cannot implement arbitrary waveforms or different keying schemes. They cannot support dynamic spectrum access, which I'm pretty sure Dr. Guan has been teaching you how important is a dynamic spectrum access in many different applications. And there is lack of ability to react on frequency and waveform diversity basis on the interference jamming. So it's not possible to build devices that can deal with the jamming or other types of noise or other types of interference that can be generated by man-made noise or by the nature noise itself. Also, most of the architectures out there, they have flat architectures, so you cannot create multi-layer networks. You cannot, and there is no support for heterogeneity. So you cannot have multiple heterogeneous devices inside one network like we have it in the modern internet. So overall, it's completely incompatible with the standard internet, and you cannot have make those devices that we have out there today a part of the Internet of Things network that we have. So to address that, few years back, we have started actually we put together a vision in place first, which is called CNET underwater networking. And the vision that we have with the CNET underwater networking was to have software-defined network systems and advanced AI algorithms for underwater communication services built on modular hardware, modular architecture. So in a sense, we would like to have software-defined capabilities and AI algorithms running on flexible, reconfigurable modular architecture. And in this way, we can address all those varying needs and varying channel effects that we have discussed. Beyond the the reconfigurability capability. This technology also enables high-speed data rates. We've been also working on building a full-stack internet-compatible networking, modern software-defined architectures, mesh networking capabilities for mobile and static elements. So you can think of underwater unmanned vehicles or some fixed sensor nodes. We've been also developing AI-based control and data analytics that you can run on the devices themselves or on the edge. And overall, this was aiming to create a flexible, scalable, secure, robust, resilient networks in underwater. And we were lucky that this project has been funded by NSF. So this is a project that has been run in collaboration with 4 PIs from Northeastern University, and was focusing on developing this open programmable platform to have these capabilities that we have mentioned, to realize that the things that we have mentioned. And in this way, it will enable the development, prototyping, and testing of next generation waveforms, networking schemes, next generation underwater applications, and also creating fixed and mobile nodes. So this is a architecture that we are working on deploying using these CNET platforms, where you can have, you can think of this as like a underwater acoustic networking playground where you can actually have different devices communicating and being tested, and that's kind of what we're trying to achieve. So going a little bit more details on the CNET project, a little bit of the primitives and the principles of the project and what we have been developing. The CNET has an open architecture. So what it means an open architecture is that you have a programmable software architecture. So that means is that you can add or update functionalities at every layer of the protocol stack. You can operate at every layer of the stack. So you can decide to do a medium access control development or a network protocol development. You can change or hide the implementation details of each layer. So you can use some existing physical layer or medium access control layers to test different parts of the architecture. You can implement cross-layer strategies. You can reprogram the physical layer that could be online or offline. And these devices that we were building, we were aiming to have support for native Linux operation system. So in that way, we can actually use all these native Linux operating applications, including the internet architecture. The other aspect of the open architecture is the hardware reconfiguration and swappable frontend. So what it means is that with the hardware reconfiguration, we can actually have seamless integration of different transducers. So just to give you a sense what transducer means is the acoustic antenna. Actually, it is the device that is converting electrical waves into the sound and acoustic waves, and vice versa. So it can also convert acoustic waves into the electrical waves. And the important part why you can actually seamlessly integrate different transducers is there is actually not one single transducer that can cover all these bands that we have in underwater acoustic domain. So most of those transducers are very much focused into one part of the band, which is much different than what we have in the RF domain. Even though there are different antennas covering different parts, it's much larger bandwidths. The other part of the reconfiguration and swappable front ends, it's also creating an operationality over different frequency bands. And it is another aspect that we were looking into, also wirelessly recharge these units using ultrasonic and acoustic waves. One other principle and one other feature that we have achieved with this project was the spectral agility. As I was telling you, we were aiming to use wider bands, including the ultrasonic regimes that can go from lower tens of kilohertz to few megahertz to reach short and medium range links. And with the spectrum agility and the reconfigurability that we have, we can do a trade-off between the distance and the data rate. So we can actually pick what distance we would like to go, and accordingly we can get the maximum data rate possible and use the maximum bandwidth possible with that flexibility. So in a sense, we have the capability to process large bandwidths of data in real time and achieve high data rates. And we have some publications on that using unprecedented size bandwidths for underwater domain, which was like few megahertz of data processed in real time and creating a short video transmission, a short distance video transmission. To look into the building block of this project and the basic development device is what we call the white box CNET modem. White box means is whatever you can think of a black box, it's right opposite of it. So it's completely open, programmable, and you can actually know what is going inside. You can adjust it. It is a flexible communication platform. As I was telling you, it is fully programmable, has MIMO capabilities, can run AI algorithms on the board, can be easily integrated to AUVs and ROVs, and can get you high-speed data rate capabilities. And you can see some of those data rate points that we got. So we've been testing different ranges and different data rates, and you can see that in the short ranges, we can do up to 1.5 megabits per second. In the medium ranges, we can do 200 kilobits per second. And in the longer ranges, that is few kilometers, we can do 8 kilobits per second. So this is like 8 to times more than what is existing out there today. Another important part of that project was to develop ultra wideband ultrasonic front ends. As I was mentioning, using the existing transducers, which are piezoelectric materials, we have quite a bit of limitation. We have quite a bit of limitation in terms of in terms of bandwidths, flexibility, and also when you like to combine them, these are much larger devices. So one of our PIs, Professor Rinaldi from Northeastern University, has been working on creating miniaturized PMAT technology base, which is a piezoelectric micromachine transducers, to create ultra-wideband ultrasonic front ends that can get high data rates and accordingly can enable also spectrum agility and can also get a MIMO and beamforming capability. So you can see a small SMA connected wafer here, and this wafer, I believe, has 100 elements on it. So you can actually have 100 by 100 MIMO capability using that small device, which cannot be done with that size with the real transducers that we have out there. So without going too much into the weeds of it, I would like to give also a little bit of brief overview of what the architecture looks like of the CNET device and what is the principle that we used here. So the hardware architecture of CNET has the principle of doing a modular design with standard interfaces. So you can think of like standard analog and digital interfaces. So if you would like to swap out or change a part of the, if you would like to improve a different part of the module, you can actually change it. Or you can upgrade the design because all of those connections are with standard interfaces. So you don't need to redesign all the modem itself, but you can design and upgrade different parts of the modem. And we have 6 basic modules in this design. We have a main module where we are running the operating system and also the programmable logic. So it is based on a Xilinx system on chip that has both the processing system and the programmable logic on a single chip in an energy efficient way. We have a converter module where we have high-speed ADC and DAC units. We have communication module, which has the receiver and transmission amplifier systems, as well as matching circuitry to match the impedance of the transducers, different transducers into our devices. We have also a power and signal module where we have set of connectors to distributed signals all over the board, all over the modem itself. And then we have a sensor interface where you can put plug and play different sensors to test different items. So you can have temperature sensor, pressure sensor, or any type of sensor like a CAN app. So looking a little bit more into the design, pretty much we're using a system on chip architecture, as I was telling. It gives a hybrid programmable logic and a processing system architecture. Why this is important is because we have quite a bit of data and large bandwidths to process. The processing systems cannot be able to process those data in real time, and it will start creating a delay, and it will start adding a delay on top of the already delayed signals that we are getting from the acoustic devices. So in order to avoid that, we have a hybrid solution where we have processing intensive communication protocol sections implemented on the programmable logic on the FPGA, where you have pretty much all the physical layer implemented on the FPGA, where you can actually achieve real-time or near real-time reception capabilities and minimizing the end-to-end delay that you might get from these devices. So this is, I think, what is important from that picture, other than all these details that we have here. And if you compare that to the existing systems out there, there is a trade-off. Basically, if you will go with a ASIC system, which is an integrated circuitry that is built specifically for an application, you're great. You're basically getting the best performance because it is perfectly hardware designed, addressing that specific communication protocol. But it doesn't give you that flexibility that you would like to reprogram the things. If you will go to a general purpose processor, where it's like a standard processor that we have used in different devices or like MCUs, then it's easier to program. You can have C++ blocks that you can use in a very high level language, but you're creating that huge processing latency. And if you would like to do with DSP chips that we have out there, then you're limited on the parallelism and the reconfigurability in handling computationally intensive tasks. So overall, we believe the SoC hybrid architecture was the best to address all these requirements that we have. Looking a little bit more in detail, I think I will not go too much in detail here, but this is more like what is implemented in where in our architecture. You can see we have a zero-paired OFDM implemented on our programmable logic on the FPGA. Then we have a data link layer and time-critical medium access control functionalities implemented also on FPGA. Then if you will go onto the processing system, which are connected inside that SoC chip with AXI buses with high-speed AXI connections, then we are running all the time-insensitive data link layer operations, like different medium access control operations, as well as routing and application layer that will complete the whole protocol stack that we have. So to go a little bit more in detail, here is our main module. So this is a MicroZ development board. So this was what we have used in our initial design as a base, as our main module. It has a Zinc SoC and a bunch of different features. Obviously, I'm not going to go in all of these, but this is relatively a small chip compared to larger FPGAs out there, and it gives you a rich set of I/O peripherals that you can use. We have the converter module executed. We have a 14-bit ADC device, which can get you up to 6 megasamples per second, and then we have a digital converter that can get you 50 megasamples per second. This goes with a 100 ping header connector connected to the main module that I just presented and create that part of the base of the module that we have. Then we have different communication modules. We have different TX and R exchange without going too much into the detail. We have the signal and power modules, which is distributing and putting all these architecture together, which covers and creates a tube size modem that you can put it into a pressure rated module that you can actually deploy into the ocean. which I will show you a few pictures of it from our deployments. Looking a little bit into the software architecture, I believe I already mentioned some of those features, but overall, it's an open source, modularly configurable architecture. You can add update functionalities that I was mentioning. And I think one thing that I haven't really emphasized before is you can also use these devices as a full-blown SDR platform. In a sense, you can actually use GNU radio, like what you can do with the off-the-shelf RF software-defined radio modems like USRPs. You can actually use these devices to test and develop different protocol stacks that you have implemented in the GNU radio, which we believe is a very, very strong tool for development. In addition, I would like to show you here. So this is a little bit more in details, like how much of the resources that we are using with the current design that we have. We have different flavors of designs. But I think one important thing that I would like to show you here is you can also use those devices as almost like a network interface card that you have it on your device. So you can actually see it here that you can have the CNET modem appear as a network card, which you can actually pick and use it as a standard interface to your device. And in that sense, it could be a completely end user device. You can implement your routing and applications using this underlying modem, or you can actually work on the protocol stack and deploy and enable different things using that. I would like to show a few results and few pictures and few developments that we have done. So this is the final deployed modem. As you can see, it's in a 4-inch tube. This is approximately, I believe, 40 to 50 centimeter tube length. And this is what we have deployed. So this is a few pictures from our deployments that we have done in the Boston Harbor Marina, where we have different bit error rates and SNR curves underneath. So we have tested at first in a lake experiment, actually in Lake Erie in Buffalo, where we have 200 meter sling, and then we had reached almost up to 250 kilobits per second with some decent bit error rate. That is around 10 to minus 5 bit error rate, as you can see here. And then we repeat the same experiments in the ocean in very short distances where we can achieve up to 520 kilobits per second with some 10 to minus 4 bit error rates. So these are all very good results that hasn't been achieved before, and that's showing what high data rate means if you would like to do this if you would like to use these devices in the underwater environment. We have done also a few other experiments showcasing the real-time reconfiguration capabilities. So in this specific experiment that we have here, we've been switching the guard intervals. So we were using different guard interval sizes to address different multipath spreads. You can see that by packet, we can change actually the separation between the individual packets that we have in the system. And this is the recording of it. Another experiment that we have done, as I mentioned at the beginning, we've been also working on the wireless power transfer and wireless charging of these devices. So this is initial results that we got, and this actually has been published recently, is wireless power transfer that we have done in a water test tank. So we have actually charged those modems using different transducers, using a beamforming scheme, and can get up to a few watts of power that can go and charge the batteries of these devices. And I believe in this specific case, we were like getting up to 1.4 watts transferred wirelessly into those devices. We had few other results that using these MEMS transducer that I mentioned, we actually were instead of putting them into the waters, because you can see that they have SMA connectors, so they're not perfectly waterproof. So we used a tissue phantom, which was mimicking an underwater channel. And we have used some 500 kilohertz bandwidth where we can achieve a promising 600 kilobits per second with 10 to minus 5 bit error rates in this short distance. And we were actually be able to send some real-time video using this very large bandwidth and very large data rates. Finally, this is from our experiments. You can see that we have done in the Nahant at the Marine Science Center of Northeastern. So we have 2 of those CNET platforms deployed, and we have 2 buoys that are controlling them. And we've been testing different communication protocols in the actual ocean environment. We have also integrated the CNET platform with some off-the-shelf ROV devices, which you can see the picture of it here on the right corner. It's a blue robotic ROV, and you can see the modem right underneath that extra tray. And what we have done in the pool, we were testing and we were getting recordings on how the modem can operate on mobile devices and how we can address the Doppler effect specifically. And we have published those results in a recent ICC paper, if you're interested in. So that being said, I will switch gears here, and then I will talk a little bit more on something different than the acoustics, but how we can actually use some different modalities, because acoustics is actually not the only modality that can work in underwater, or in a sense like a part of the underwater. So in a more recent study and research that we were working on connecting air-water devices. So as I was mentioning at the beginning of my talk, we have some underwater vehicles and some aerial vehicles that needs to be connected to each other. And today, if you would like to do that, you might need a buoy in between. And what we were doing in this project were to use visible light technology, specifically blue or green light lasers, to be able to connect and establish links bidirectionally between the air-water interface, and then can send high data rate links between those devices without requiring actually a third device that is on the surface. And why is that important? If you look a little bit more in detail, the problem here, if you need to establish high data rate and robust bidirectional communication links between those assets, you're dependent on these floating devices, which are called buoys, as I was mentioning, which has an acoustic communication underneath and then has RF communication up top. But these devices, you cannot deploy it everywhere on the ocean, obviously, right? We cannot just create millions of these buoys to be able to communicate the whole devices that we have in the underwater and then the aerial. So this needs to be a little bit more efficient, where we can actually bring those devices, deploy, and then without requiring another infrastructure in place. Another problem is that those floating devices can actually be vulnerable to environmental effects. So one actual news, it's giving for some reason, one actually interesting news is 2 fishermen was stealing a US government ocean buoy, and they were basically asking for a ransom to give it back. So these devices pretty much are completely vulnerable to different environmental effects, and also to people that would like to steal or jam them. If you look into some other approaches out there, you can use some unmanned autonomous surface vehicles, or you can use some UUVs to submerge, but these are also not completely solving the problem, as they still need to resurface a lot, or they need to basically spend too much time on the surface and losing the whole point of being submerged at the first place. If you look into the literature, there has been similar approaches published using optical communications. However, most of those studies require highly controlled test beds, precise alignments, and most of those studies were dependent and limited only to simulation data. So when you're using a laser or a specific beam, then you need a perfect alignment, and it doesn't work if you're missing this alignment. And I will show you a few results actually on that, which we were able to address by using visible light instead of precise lasers. There are also some alternative approaches to this problem, like what is called transitional acoustic RF communications. However, they are all limited by their low data rate and limited communication range due to the high attenuation of the underwater. In a sense, TARF was using radio, it's using sound waves underwater. It's creating vibrations on the surface of the water, and using a radar, it was detecting these vibrations over the water. But this technology itself requires precise alignment. It can only work with some surface waves that is less than 16 meters. And it can only work unidirectional. So it can only work with the devices that is from the underwater to the aerial devices. It cannot work the other way around, obviously. Another approach was magnetic induction, which is also another research and development project that has been going on, but this is also inherently limited due to the high attenuation of the due to the salty waters, high attenuation to the magnetic waves. So we propose software-defined visible light networking, which basically can enable robust, secure, and self-optimizing bidirectional communication links through the air-water interface. It is spectrally efficient and suitable for ocean dynamics without requiring any relay nodes. Looking a little bit more, we started first by developing a simulator. Then we have actually designed and prototyped a software-defined VLC modem, which is based on a similar architecture as our acoustic modem, which I just presented the CNET. It is composed of 3 modules. We have a main module, which incorporates a micro Z. We have DAC and ADC, which enables data streaming and recording through the VLC hardware. With the combination of the ARM processor and the FPGA inside the micro Z, the main module can provide hardware software reconfigurability with the compact packaging and low energy consumption, as I just mentioned in the CNET part. We have also power and switch modules, module interfaces with the modem. A battery unit carries along the digital and interfaces between different modules. And then we have a VLC front end, which includes a LED driver on the transmitter side. The driver is composed of a single N-channel MOSFET with the common source topology and with source degeneration. On the receiver side, we have a VLC. On the receiver side, we have an avalanche photodetector with interconnected to a variable gain amplifier. And on the back end, we can actually also connect those devices to be able to pull data in real time and operate that with a host PC or another device that we would like to operate. So we have done a large experimental study. We have looked into the different parts. Start first with a test bed. So during the water tanks experiments, we actually use 2 types of test beds. In one of the test beds, we have pre-aligned setup where the modems are pre-aligned and separated 1 meter from each other with a 6 feet aluminum rod, which you can see on the left of the picture. The second setup is where the X and Z axis variable is for some reason skipping the slides, but in the second one, we remove those poles and in a way that we can actually create some misalignment and different types of effects between the receiver and the transmitter itself. So in this way, we can actually change the distance, misalignment, and we can vary different parts of the setup to test. We start our study with a modulation scheme analysis. So the most important aspect in visible light communication is that the transmitted waves are non-coherent, which means is that you can only use intensity modulation or direct detection. This is much different from what you can have from the coherent waves where we can use where we use acoustic waves or RF waves. So this is a completely different scenario. So most common modulation schemes for such systems are on-off keying, could be Manchester encoding. However, if you would like to increase the data rate, you can also use multi-carrier modulation schemes such as CAP scheme or OFDM, DCO, or Philip OFDM. So different flavors of non-coherent orthogonal frequency division multiplexings. So during this analysis, we kept a fixed VGA gains, and we used different we compare different modulation schemes, how they work and how they are actually performing compared to each other. So first, we compared several different modulation schemes for both air to water and water to air channels. So you can see on the left two graphs. We have air to water channels. We have used 1 megahertz bandwidth in all configurations. And you can see that in most of the cases, the OFDM is outperforming the other communication schemes. We have also some results from the water to air link, where you can see that asymmetrically clipped optical OFDM, which is the AC OFDM, giving the best solution. With that being said, after getting an idea on modulation scheme and performance, we moved on the impact of the physical parameters that affect the communication link. So we have conducted different experiments using a DCO OFDM, and we have looked into the different parameters. First, we started with a distance analysis. What happens if you change the distance between the devices, and how the distance affects if you have it either on the water column or in the air column. So you can see different results. So in the first graph here, we have a fixed distance on the air channel, and then we were varying the water distance. In a sense, we were putting the device that is inside the water deeper. And in the second result here on the right, we have fixed the depth in the water, and we were changing the distance in the air. So you can see it's pretty much what you can expect. It just increases with attenuation with different distances as you're losing the intensity here with the distance. So there is no surprises on the distance. Obviously, it is well what we were expecting, and we actually cross-validate that results with our simulation models, and they were pretty much same what we were experiencing in the theoretical sense as well. Then we start studying some other less explicit scenarios where we misalign the devices. So what we have done is that we misalign the two modems to each other, that is inside the water and the outside the water, to see how this is comparing to the theoretical simulation results that we have. And you can see actually in the experimental setting, you have more spreading than the theoretical setting. So if you're doing a theoretical setting, you can only assume that you're going to have a coverage area of few centimeters only here. But in experimental data, actually, you can see that it's spreading more and more towards the sides, even though the intensity gets lower on the horizontal distances. So it can actually get you a much larger coverage area if you in the experimental domain, both in air to water channel and water to air channel. Another important factor for the air water communication link is actually the surface waves of the ocean and the seawater that we have. So in the water test tank, we have created some artificial waves, which almost reaches the 3 centimeters peak-to-peak waves. And what we have done is that we have recorded different SNR levels with, we basically investigate how the SNR changes with these surface waves. And here you can see SNR is approximately changing 0.5 dB when there is a huge wave action. So you can see that as the surface displacement, which is shown in the red, increases, you can get a fluctuation in the SNR as well, which is around 0.5 dB. But this is relatively can be negligent, as 0.5 dB would be much less compared to what is compared to a whole system. So overall, this shows that actually the surface waves do not have a large impact on this technology when you're communicating those devices, water to air or air to water. So until now, we have done all the experiments with some specific turbidity level, which was 0.09 NTU. So which was like the standards that you find it in the clear water. And this is pretty much what you have it with the drinking water as well. So in order to create and generate some turbidity, we use some zinc oxide powder, and we gradually increase the turbidity to see how this is actually changing with the bit error rate measurements. So we first put a little bit of that powder, we created a little bit more unclear water, and then we go all the way up to 70 NTU, which is much, much higher than the average low turbidity level in coastal waters. And you can see some different bit error rate results in different NTU levels. So even in the extreme level where you have 70 NTU, which is almost impossible to find in any natural environment, you still can get the bit error rates up to 10 to minus 3, 10 to minus 2. And if you will go into some more realistic water clarity levels like 25.42, which is still not a clear water, as you can see, you were still able to get almost 10 to minus 6, 10 to minus 4 bit error rates, which is actually quite impressive given how these things are looking. And I wasn't expecting to get that that much bit error rate performance. We have also done some, until now, all the measurements that we have conducted was done in a dark room to eliminate the background noise factor. So we have also done some measurements and observing different indoor lighting, how it is affecting, actually how the background noise is affecting our bit error rates. And here you can see we basically increase the light intensity in the room, and we try to observe how much signal to noise ratio we have decreased. And we have seen that with pushing the light intensity in the environment to the maximum in a room as much as we can do, we were able to get 2 dB decrease in an SNR. So this background noise is something definitely affecting, but it's not impacting the SNR as we expected as well. And obviously this can be different with the sun. Sun is not going to be the same, similar to what we have with the room lighting. So actually that will what we have done in this test as well. So finally, we want to demonstrate if this thing is actually working in the wild. And particularly, we have done this experiment in a marina here at Boston. And we have tested different settings. First, we have tested the air to water and then water to air channel with using CAP and DCO OFDM modulation schemes. And as you can see, we were able to get quite good results, up to 10 to minus 6 bit error rates with some decent SNR levels. And we were able to stream actually high data rates, which was 1 megabits per second over 1 megahertz bandwidth. So overall, this showcases is actually this system can work in the wild and can create high data rate links in this air-to-water interface and can be a viable technology for future applications. So with that being said, I would like to show one slide of one of our recent works as well. I would like to do a simple introduction. So this work we're focused mostly on using AI algorithms for improving the underwater acoustic channels. As I was just explaining, the underwater channel has high volatility, so it's changing and varying from different parts of the ocean from time to time. So it's very hard to have some fixed signal detection or decoding systems. So in this project, we were aiming to use AI and specifically deep learning techniques to train and accordingly detect different types of signals, different bandwidths, and also have automatic modulation control. So, so far we have created some different data sets with the results, with the actual data sets that we have been collecting in different environments. So we have trained our CNN networks, and we were able to actually achieve real-time performance that we can distinguish between different communication modules, and we can actually detect their bandwidth. So we can see the confusion matrix here. We can detect and identify an empty channel. We can distinguish an OFDM or a frequency shift keying from a church spectrum. So you can actually adapt and reconfigure your receiver based on what signal is coming in real time using this automatic modulation control. And you can also understand which bandwidth is using, so you can accordingly adjust the bandwidth that you need to use as well. So we believe this would be a very, very strong tool going forward. And this is a work that will be published. This is actually a preliminary result, which is not published yet. So, but we are very much encouraged with the initial results that we got. So I think that being said, I will wrap up that part of the story, and I will briefly mention what we are doing also in the company, and specifically in the underwater domain of the company, where we call HydroNet. So HydroNet, it's very much spinned off from that idea that we just talked about. It's using all those principles and then aiming to actually bring a modem to the market. So in a sense, HydroNet's mission is to bring the internet underwater and empower it with AI-driven software-defined technologies to enable the blue economy. Very similarly to the CNET architecture, we have a software-defined networking platform and an edge computing device. In addition to what I was just mentioning, it can also have different capabilities, can do sensing, AI analytics and control, and can act as an intelligent edge device, which it can run different algorithms. But HydroNet is not only a modem, it's actually much more than a modem. It's a suite of software-defined network systems and advanced AI algorithms for underwater communication and sensing services built on a proprietary architecture. So it can get all those nice features like high-speed data rates, AI-based control data analytics, and can also get some unique containerized architecture like the cloud-native containers architecture, which really enables new applications that can be enabled, which can be used with this technology. We've been funded and getting traction by different entities. We actually were working with DARPA on that specific project and get quite a bit of recognition and accelerated programs all around the United States and also world. So we have some also Italian accelerated programs that is supporting our research. And this is actually a reality already. So we have deployed these modems in the pools with some ROVs. We can test the communication link. We have deployed them in a very cold day here in the Boston Marina Harbor. You can see how freezing it's around. It was actually below zero, I guess, that day. And then we have been testing also in Narragansett Bay with the Navy Underwater Warfare Center. And we have recently also did a demonstration in a US Navy exercise called Trident Spectre, where we actually showcased underwater wireless video streaming from the bottom of the ocean to a device that's on the surface of the ocean. So if you're interested working in this technology, or if you're interested also working in general Bionet sonar, we'll be happy to also talk to you, and we can have a chat about that as well offline. So thank you very much. I will be happy to answer if you have any questions. I believe that was quite a bit of material to digest, but I hope that the message conveyed clearly about what is required and why underwater communications are going towards a software-defined future. Thank you.